Hello. In our previous discussion on the Compton scattering, we had obtained the expression for the difference in the wavelength as well as the kinetic energy term for the electron. Now, the difference in wavelength consisted of a term which was given as the Compton wavelength lambda c, and we also obtained the kinetic energy for the electron, which we obviously had the case that it depended on the incident energy of the photon, that is h nu naught. Right down there, the formula that you see, that is k is equal to h nu naught. H nu naught is the energy of the incident photon, followed by the other terms. Lambda c over there is obviously the Compton wavelength. Now we also discussed about the modified and the unmodified lines. The unmodified lines are hardly observed. We'll be discussing that as well. That is the Thomson component, while the modified lines that we observe have a different wavelength. The wavelength in the Thomson component is not observed. It's nearly the same for the photon as it was in the case of the incident photon's wavelength. The incident photon had the corresponding frequency, momentum, and energy as nu naught, p naught, and e naught, as we can see in the given figure, the schematic diagram that we have drawn over there. And after scattering, it has been scattered through an angle theta with respect to the incident direction, and in that direction it now has a frequency nu 1, and the corresponding wavelength is lambda 1, which is obviously greater than the incident wavelength, and as a result of that we are getting the del lambda, that is the increase in the wavelength that is obtained to be positive, and that increases with the angle of scattering. Now, as far as the electron is concerned, the electron initially was at rest, and because it was in supposedly a free electron that is present near about the atom in which we are making the photon to fire, or we are firing in the photons, and the recoil angle of the electron is phi, and it goes down as you can see in the figure, and it has now a momentum pe and the energy ee. So we had obtained the energy. Now we will be extending our discussion on this topic. For that, let me take a fresh page for you. Now remember that formula. I'll be writing that down once again. So we have the value of k to be equal to, let me use another ink. So the value of k is equal to the h nu naught. Yes, I remember that. H nu naught 2 times of lambda c, 2 times of lambda c sine squared theta over 2 divided by we had the first term as lambda naught plus 2 times of lambda c, again the Compton wavelength, sine squared theta over 2. Let's just see if I've written it correctly. I may be wrong at times. I hope not. So this is absolutely accurate. So now with those values that I have over there, what I can do is I can divide that factor at the top, the numerator term, and take it below the denominator. So what we have is h nu naught stays alone at the top, and at the bottom we have lambda naught plus 2 lambda c sine squared theta over 2 entirely divided by that term which has come down, 2 lambda c times of sine squared theta over 2. What that does is we have h nu naught and the first term over here. Now we denote, or we introduce a new term which is alpha, a shorthand notation which is easier, which will come handy to write the expression, because the expression won't be that bulky, won't look bulky. So in that case, we have the value of alpha to be equal to lambda c over lambda naught. Now if you remember, lambda c over here was h over was h over mec. So h over mec, and lambda naught is simply going to be equal to h over p, that is in case of the p naught, h over p naught. Now instead of taking it as h over p naught, we would probably take it as c over nu naught. So c over nu naught, it's the other way around because it's in the denominator. So this is now equal to h nu naught times of mec squared. And so now this over here, what we are getting is the lambda naught divided by this entire term at the denominator, coming back to the equation once again. And so lambda naught over lambda c is going to give me 1 over alpha, and we have a 2 over there. So this is 1 over 2 alpha, the reciprocal of alpha obviously, and sine squared theta by 2 multiplied to that, we can just take it as cosecant squared theta over 2. This can be taken into account, and the second term cancels out completely, so we have 1 over there. Now this is the value of the kinetic energy term that we have obtained, and this is in terms of the alpha that we have introduced over there. Now going back to the case of the electron, now if we wish to determine the angle of recoil in that case, so let's consider the figure once again. We align the action that has taken place, the incidence of photon, to be along the x-axis, and so the corresponding perpendicular axis to it is going to be y. Now this is the momentum of the incident photon, and it has struck the electron. As a result of that, the electron has recoiled through an angle that we have denoted by phi, and the angle of scattering in this case has been, that is the scattering of the photon, has been at an angle of theta with a momentum p1, the new momentum. This is pe, the momentum carried by the electron. Now with these things available to us, what we can do is, along the x-axis we can have an equation. Now conservation of linear momentum tells us that along the x-axis, following the conservation of linear momentum, of course, we have p naught simply to be equal to the sum of the two terms, that is the cosine component of the p1, which is p1 cosine of theta, and the cosine component of pe, that is pe cosine phi. So this is the case in the x-axis as per the conservation of momentum. And then we can just rearrange this, because we want to obtain the angle phi over there. So we can take it as pe cosine phi is now equal to p naught minus p1 cosine of theta. Well, as far as the p is concerned, we have h over lambda, the corresponding de Broglie equation for the momentum. So from that we have h over lambda e, h over lambda naught, h over lambda 1. But instead of taking lambda, we can take it as hc over nu e. So not hc over nu e, but h over c times of nu. So this would have been h over lambda e, but lambda e, as you know, is simply c over nu e. So that being in the denominator, we take the reciprocal of that, and this is cosine phi. Similarly, we will be having h over c terms over here as well, and we will have the nu naught, in this case the frequency of the incident photon, nu 1 the frequency of the scattered photon, times of cosine of theta, and the h over c can get cancelled out on both sides, so we have the equation nu e cosine of phi to be equal to nu naught minus nu 1 cosine of theta. Similarly, in the y-axis, if we consider the momentum conservation, then we will have P1 sine theta at the top and PE sine phi at the bottom, and they will be equal owing to the conservation of momentum. And so, because we know that we are eventually going to end up with the frequency term, so let me write that directly for you. I hope it won't be a problem now, that nu e is what is going down, sine phi, and on the other side from that P1 sine theta we have nu 1 sine theta. Now if we take the ratio of the second term of the y-axis term with respect to the x-axis term, then what we get is, from these two, what we are getting is that we have tan phi, the tangent of phi, that is the second term divided by the first term is giving the nu e cancels out, and sine phi over cosine phi is going to give us tangent of phi, and this one at the top will go as a nu 1 sine theta divided by nu naught minus nu 1 cosine theta. So now we have the angle. In this case the angle is tan phi, and that is equal to that value that we have over there. We can have a much more efficient expression for our better understanding. So let's get into that. For that we will have to refer to the case of the difference in wavelengths. And what we had initially is that if you go back a few pages, and you will see that we had obtained the difference in the reciprocal of the frequency, which has come out of the difference in the wavelength. So 1 over nu 1 minus 1 over nu naught was equal to h over me c squared times of 1 minus cosine of theta. This is what we had. I had actually given you c times c divided by nu 1 and minus c divided by nu naught. Well, the c was multiplied there at the top, and we had h over mec, only a single c, but that c has gone down again, so h over mec squared we have over here. Simplifying this, what we get is we get nu naught minus nu 1 times of nu 1 times of nu naught is equal to h over mec squared 1 minus cosine of theta. Right? And if we just cross it over, cross multiplying, what we get is we have nu naught simply to be equal to, that has cross multiplied, so we have h nu 1 nu naught over mec squared 1 minus cosine theta, and onto the other side we have nu 1. Now if we are to consider this expression over here, if you notice down in the denominator term we have nu naught minus nu 1 cosine of theta. So what we do is we take nu naught minus nu 1 cosine of theta over here, and we do the same thing over here. We introduce a nu 1 cosine theta term over to the right hand side as well. So we have mec squared 1 minus cosine theta plus nu 1 minus nu 1 cosine theta. So what that does is we can take the nu 1 as the common term from the last two terms on the right hand side down below there. So we will have another 1 minus cosine theta, and further we can take that 1 minus cosine theta as the common term between the two. So let's do that. So if you remember this formula, I hope you're writing it down so that you don't miss it. I'm going over to the next page. So if we had the last term, that is nu naught minus nu 1 cosine theta will be equal to that term over there. And if you observe, h nu naught over mec squared is simply alpha. So alpha times of nu 1, nu naught minus nu 1 cosine theta is equal to h over mec, h nu naught over mec squared is simply alpha times of nu 1 minus cosine theta. Then we had another nu 1 minus cosine theta. So on the right hand side we simply have alpha, nu 1 goes as the common term, so does 1 minus cosine of theta. So we have simply alpha plus 1 nu 1 minus cosine of theta. Now this expression over here, what we had is tan phi. If you consider the tan phi equation, we have a nu 1 sine theta over that term that we have just obtained in the left hand side. So what we do is we divide it with a nu 1 sine theta, because that was present there at the top. So we have got that in the denominator. So as you can see, that tan phi equation that we had over there is equal to the factor that we have just obtained the reciprocal of. So this is the reciprocal term of that factor. So this is going on the left hand side is obviously going to be 1 over tan phi, or cotangent of phi. So this is nu naught minus nu 1 cosine theta divided by nu 1 sine theta, and over here we have alpha plus 1 nu 1. Well, the nu 1, that nu 1 can go down, that nu 1 has gone down over here, so we don't write that. And we have 1 minus cosine theta. Well, that can be taken as simply 2 times of sine squared theta over 2. And because we have got another factor sine theta over here, well, that can be 2 times of sine theta over 2 cosine theta over 2. So this one of the sine theta over 2 terms cancels out, the 2's cancel out, and what we get is simply 1 plus alpha, or alpha plus 1 tangent of theta over 2, and this left side is simply cotangent of phi. So what we get to know is that the angle of recoil of the electron, that depends on the angle of scattering, that is theta. Angle of recoil depends on the angle of scattering, which is of course theta. How does it depend? Well, you can put the values over there. The angle of scattering can be 0. So if it is 0, means it is just pushed head on, or it moves along its line, it continues to stay in its line, it is powerful enough to knock the electron and it travels along its own line. In that case, we'll have this factor over here to be equal to tangent of 0. Now tangent of 0 is simply sine 0 over cosine 0, which means it is going to be 0. And so this right hand side term entirely goes to 0. So cotangent of phi goes to 0. cotangent of phi going to 0 means that we have tangent of phi to be infinity, or we simply have phi to be equal to 90 degrees. That means the electron will be knocked off uh, at right angles to the direction of motion of the incident photon. Then again, if we consider the case where theta supposedly is 180 degrees, which is the case when it bounces back, it retraces its path, it is scattered backward. In that case, we have a tangent of 180 degrees, which is again going to be 0. But it's not tangent of 180 degrees, but it's tangent of 180 over 2, which is tangent of 90. Now, tangent of 90 is going to be infinite. Infinite means cotangent. Well, in this case as well, cotangent was equal to infinity. So cotangent in that case is going to be a 0, and because that is going to be 0, with tan phi going to no, that actually that was correct, that was 0, that's fine. This is infinity because we have the tan 90 term on the right hand side now. So cotangent is going to be equal to infinity, or tan phi is going to be equal to 0. Now, tan phi is equal to 0 means phi is obviously going to be equal to 0. That means the recoiling angle will be along the same line, which means the incident photon goes in, strikes the electron, and it retraces its path backward, while the electron is further projected in the forward direction. This is what happens in this case. While in this case, it approaches the electron, it strikes it. Now, the photon initially it continues in its path, whereas this electron over here, it is recoiled through an angle of 90 degrees in that case. So this is more or less the relation between the angle of scattering and the angle of recoil. Now we can go the other way around. We can obtain an expression for the angle of scattering with respect to the angle of recoil. Let's do that. And in order to do that, what we do is we reverse or take the reciprocal of the angle term. So in this case, we had cotangent of phi, and on the other side we have tangent of theta over 2. What if that comes down? That is, the tangent of theta over 2 goes to the other side in the denominator. So this expression can now be written as cotangent of theta over 2, because that has gone down, and this fellow, that cotangent of phi, that has gone to the denominator of the other side, so that will be tan phi in the numerator. So we have 1 plus alpha tan phi. Now with that thing, what we get is the cosine of theta, just an extra term that I'm writing here, cosine of theta is equal to 1 minus 2 sine squared theta over 2, trigonometrical identity, and that is equal to 1 minus, well, this can be written as 2 over, this is a cosecant square of theta over 2 in the denominator, because the sine squared can go down and in the denominator it becomes the cosecant, and the cosecant term is simply cotangent squared theta over 2 plus 1. Cosec square theta is equal to cot square theta plus 1. So we have this cos theta to be equal to, this is to be equal to, from this we are getting it, cosine of theta is equal to 1 minus 2 divided by, now if you have that cotangent squared theta over 2, now remember what is cotangent squared? Cotangent square theta, cotangent of theta over 2 is this. So the square of that is going to give us 1 plus alpha squared tan squared phi, and that is added to 1. So this is the relation between the relation of the angle of scattering with respect to the angle of recoil, that is theta with respect to phi. Now, if we consider the case of kinetic energy of the electron once again, that will be maximum when the kinetic energy when the electron, it starts off in the forward direction of the beam, that is phi is equal to 0, and we know that, so this is the case of maximum kinetic energy of electron. So this is when phi is equal to 0, and we know when phi is equal to 0, phi is equal to 0 when theta is equal to 180 degrees. This is exactly what I have written over here. We have obtained that. So theta being equal to 180 degrees, we can put the value over there for maximum kinetic energy that we had. The kinetic energy, in this case it is maximum, is equal to, well, it had only h nu naught, and this term over here, that is 1 plus 2 times of, if you go back, in this case that boxed term we have, and for theta is equal to 180 degrees, we have cosecant square of 90 degrees, and that is going to be equal to 1. So we have 1 plus 1 over 2 alpha plus 1, or 1 plus 1 by 2 alpha. And that, solving that, we get simply h nu naught. The 2 alpha term comes up, and in the denominator, taking the LCM, we have 1 plus 2 alpha. Now if you again recollect, h nu naught over mec squared was alpha, so we have a 2 alpha here. Now where did that mec squared term just appear? It cannot just appear like that, so I have to multiply an mec squared so as to divide an mec squared, just to bring in that extra alpha. So this term over here is equal to alpha, and that alpha goes in and multiplies with that bracketed term. So mec squared, in that bracket we had 1 alpha, now we have 2 alphas multiplied together, so we have 2 alpha squared, 1 plus 2 alpha. So this is the expression for the maximum kinetic energy that can be possessed by the electron. Now we can discuss a bit about the unmodified line. Now the modified line had a different wavelength frequency that associated with it, that is nu 1, lambda 1, all of that, which is the Compton component. The unmodified line, which is the Thomson component, that didn't have any change in its, or that didn't have any modifications, and hence the name unmodified. So both these components are present during the scattering, Compton scattering, but this goes unnoticed. The unmodified term, that goes unnoticed. And why is that? Well, it's because of the conditions that make it happen. What are the conditions? Well, the unmodified line is actually the result of coherent scattering of incident radiation by the inner electrons of the atom. Unmodified line is due to the coherent scattering of the incident radiation, that is the photon that has been made incident radiation, which is of the form h nu naught, by the inner electrons of atom. Now these inner electrons that we consider over here, they are tightly bound to the atom, and the energy that is provided by the colliding photon, which is h nu naught, the energy that we just expressed or wrote it down there, that energy that is provided by the colliding photon, that may not be sufficient to unbound these electrons, because they are inner electrons, they are strongly bound to the atom. And therefore, when that is struck by the photon, the entire atom to which the electron is bound, that tends to recoil. And as a result of that, the mass of the electron is then effectively the mass of the atom in that case. So instead of taking the mass of the electron, because the entire atom is recoiled, and that is eventually because of the case that the electron is tightly bound to the atom, instead of the mass consideration for the electron only, we have to consider the mass of the atom as a whole, which is obviously quite greater than the mass of the electron. So now if we observe the case of the difference in wavelength, the formula now is h over, it was me, that is the mass of the electron in the previous case in Compton scattering, but in this case, with the electron being tightly bound to the atom, the entire atomic mass has to be considered, which is quite large, and therefore this difference, which was quite marked in case of the Compton scattering, in this case, as the denominator term is quite big, this factor results in this going unnoticed, or this being not so effective. The del lambda term, that is the difference in wavelength in this case, is a very less, and hence goes unnoticed. It cannot be detected although it is present. This happens, the unmodified line is there, but it cannot be detected because of the factor that the electron is tightly bound to the atom and the atomic mass is considered as a whole, because the recoiling here, or the obviously the recoiling takes place in case of the entire atom, which is not that big that it will shake the entire system of it. So that's more or less about the Compton scattering. We will be discussing a few numerical problems in the topic in the upcoming videos. Till then, thank you for watching.